Welcome back to some more geometry. We are starting chapter 3. Welcome all back. This is where it gets a little different. We're looking at some new different type of math now. So this chapter is on deductive and inductive reasoning. So one is based off assumptions, one's based off rules and facts. So let's go ahead and start it. We're going to start with the inductive reasoning. So inductive reasoning happens when you see a bunch of examples happen, and then you make a conclusion based on that. Could your conclusion be true? Yeah, but is it always true? Not necessarily. So in class, we talked about how you can see the same actions happen. So we say, like, hey, a person made a 10 on their test, then he made a 20 on their test. So based off the two examples we have, we can probably guess that, hey, maybe on the next test he'll make a 30. These are just specific examples that we see to make a conclusion. It doesn't necessarily mean that he will. So, for example, here, Jennifer leaves school at 7 a.m. So, if Jennifer leaves on time every time, and then she leaves at that time, let me fix this real quick. There you go. If Jennifer leaves at that time every single time, we can assume that she'll be at school on time if she leaves at 7 o'clock. Is that true? Maybe, but is it always true? No. I mean, there's things that can happen. There's things that can happen. That she can run into traffic. She can run into traffic. A train can be in the road. She can be in an accident. These are different. There's different factors that can happen that can cause her not to be at school on time, leaving at 7 a.m. So, this is just, again, we see something, a pattern, and we make an assumption. So, for example, this next one, a chair at this house in the living room, it's red. Also, the dining room chair is red. And also, I noticed that their bedroom chair is red. So, can we make an assumption? Yeah, we can say two things. You can say, hey, all chairs are red in their house. So, all chairs are red. Or we can also say that their favorite color might be red. Chairs are red. Or we can say, favorite color is red. Color is red. Sorry for my bad handwriting. This little pad's been kind of acting weird. Alright, so that's what inductive reasoning. You just see a pattern and make a guess on that. Now, other things that happen, more mathematically speaking right here. We say, hey, the product of two numbers. You say, like, well, what do I do with that? So you're going to have to make some assumption based off what we know. Remember, the product is the answer to a multiplication problem. So we got two odd numbers. So let's pick some just random two numbers. Do 5 and 7. 5 and 7. 5 and 7 give us 35, okay? Let's do 11 times 3. That gives us 33. Let's pick 7 times 9. 7 times 9. That's 63. So what assumption do we make about all these odd numbers? Hey, they are all odd. That is what we call a conjecture. The conjecture is the actual, if you didn't get it, it's the conclusion that we make, the assumption that we're making based off the information that was given to us, or the question that was asked. So the question was asked, what assumptions can we make about every single product of two odd numbers? They're all odd. Okay. What about this right here, the relationship between A and B? The relationship between A and B, if AB and BC, if AB equals BC and B does not equal 0. So that means some value A, oh, there's a bell, some value A times, let's say, 5 equals 5 times some value C. What can we say about this? Well, hopefully you got the same conclusions, and let's work that out. So we got this written out, divide by 5. We end up getting A equals C. So that's the relationship. They are equal. They have to be. They are equal. All right. What about the relationship between two intersecting lines that form four congruent right angles? So 4 congruent angles. So I have two lines that intersect somehow. So let's just kind of get some random lines. So I got two lines that intersect it. Well, these aren't all congruent because I know for sure that's congruent to that because they're vertical angles. But these two are congruent to each other. But all 4 are not. So how can we make congruent lines? So hopefully you remember from chapter 2, we talked about certain set of lines. A certain set of lines that are perpendicular. Yeah, because they form 4 right angles. And that means all 4 angles are congruent to each other because they're all the same. So the relationship was they are perpendicular. statements. Okay, so that is the relationship. So we're making our own assumptions based off the facts that are given to us. Again, these are assumptions. Are they always true? Not necessarily, but are they mostly true? Most of the times. But what happens if they're not true? Good question. Let's talk about what we call counterexamples. Counterexamples happen when you can make at least one example that proves the whole thing saying wrong. So when we make these blanket conjectures, we are saying in absoluteness, so in total absoluteness, this is true for everything. So for example, all prime numbers are odd. True or false? Well, that's technically false because again, we're saying all, or saying every single one. Well, the number 2 is a prime number, so this is a false statement. Because the number 2 is prime, but it's not odd. Right? All current American dollar bills are green. All. True or false? Hey, that's false as well. Somebody pointed out we have the $10 bill. That is kind of tannish. And then, surprisingly, somebody had a 50. They say, hey, a $50 bill is not green. It's kind of pinkish. It has some green in it, but it's kind of pinkish at the edge. That's true as well. All freshmen are cheaters. Some of you guys jokingly said true, but we can't necessarily say that because we're saying in absoluteness, we have met every single freshman and we had deemed them cheaters. So that is false as well. All birds have wings. That actually is a true statement. So sometimes there is no counterexample because one of the characteristics of birds is wings. So all birds do have wings. So let's kind of look at this how you'll see it in the homework a little bit more. So Gabriel here started training with the track team 5 weeks ago. During his first week, he ran 0.5 miles. Now the next 3 weeks, he ran 0.75, 1, and 1.25 at each practice. If he continues this pattern, how many miles will he be running at practice during the 7th week? Well, let's kind of sit down and look at that. So 1, first week, he ran 0.5. Week 2, he ran 0.75. Week 3, he ran 1. Week 4, he ran 1.25. Alright, so that's where we are. So then we can go ahead and assume, based on the pattern, so the conjecture, let's make a conjecture real quick. It's going up by 25. So every week, he increases by 0.25. So that's how much he's miles. That's how much he should be increasing. So technically, based off our conjecture in our pattern of connection, we see that at week 5 he should be at 1.5. At week 6 he should be at 1.75, and then at week 7, hopefully you guessed it, 2 miles. All right. Now this one right here, the relationship between the area of a square with sides x and the relationship between a rectangle with sides x and 2x. So let's kind of just draw a square. So we got a square right here, has side x and x. So if you remember, to find the area of a square, we take side times side. So x times x is x squared. On a rectangle, the pattern's the same. Base times height, length times width. So we got a height of x and the base of 2x. We multiply those two, we get 2x squared. So we have the areas now. So let's look at these areas. We got x squared and then 2x squared. All right, so if you had a guess, what you gonna do right here? So let's look at them. They both have x squared, but this one has a 2. So what does that 2 represent when you're looking at the area? Well, it says that the rectangle is twice as much as the square. Now, the way we kind of get that conclusion is, let's put in a number. Let's say this is 5. X is 5. So we got 5 times 5. We get 25 for this one. We do 5 times 5 is 25 times 2 is 100. Not sorry, 50. 50. All right. What if we put a 10? What if we say it's 10? I'm going to change the color so we get the number. What if we say the sides are 10? So 10 times 10 is 100. So we got 100 over here. Well, 10 times 10 is 100 times 2 is 200. So as you can see, it's always going to be twice as much because of that 2. That's the only conjecture you can really truly make about this. And we're looking at the conjecture. We say, hey, what's the biggest difference and the obvious difference here that's happening? The pattern. Because they both share x squared. That was something to say, well, they both have x squared. It's true. They do. But what's the difference? That's where the pattern kind of come to like, oh, this will always be twice as much because no matter what number I put in here, that same value will be over here, but then times 2. So that's 3.1 in a nutshell. If you have any questions, feel free to ask. Bye.